Okay, good evening, everyone. Good morning in the Philippines. Welcome to our bi-weekly seminars, PAASE bi-weekly webinars. As you know, we have made Friday mornings in the Philippines and Thursday evenings in the United States as the home for this webinar series. And so today, I'm very excited to welcome our speaker. I actually met him in person last year at the APAMS in Florida. And so when we were looking for speakers, we thought, hey, we need to invite Christian because he is indeed one of the rising stars of organic chemistry and one of our rising stars of PAASE. Christian, member ka na ba? So we have to make him a member if you're not. Anyway, so, Fab, can we move the slide forward, please? This is, hang on, I'm just moving my stuff. Okay, so, to introduce Christian, he was born and raised in Bangi, Ilocos Norte in the Philippines. He moved to Manila and completed his bachelor's degree and master's degree in chemistry from the Far Eastern University and Ateneo de Manila University. In 2016, he received his PhD in organic chemistry at the University of Connecticut. And so there was instant connection between Christian and Leia Tolosa, who is one of our former presidents, the past president of PAASE and very active member of PAASE, who also got her PhD at University of Connecticut. This was followed by a postdoctoral fellowship at the University of Michigan. That is also where I actually did my postdoctoral fellowship, so there's instant connection again, and at the University of Utah. During his graduate and postdoctoral studies, Christian made significant contributions in the area of transition metal catalysis and organic synthesis with over 30 publications, and he was recognized with the Connecticut Chemistry Research Award. He also received an ACS Division of Organic Chemistry Award, which is prestigious by itself, a Boehringer Ingelheim Mannheim PhD Fellowship, and recently one of the most coveted fellowships for anybody who's starting their career in the United States, an NIH Pathway to Independence Investigator Award. In 2022, Christian started his appointment as a tenure-track assistant professor of chemistry at Northwestern University, where his group works on the utility of organic synthesis, transition metal catalysis, and molecular electrochemistry towards the discovery of sustainable organic reactions and the development of next-generation organic-based redox flow batteries. So, Kristen, without further ado, I will give you Kristen to give his seminar. Feb, can you go back to where the title is? Never mind. Where is it? But anyway, Christian, take it away.
Thank you so much, Marge. Thank you so much, Dr. Pena, for the wonderful introduction and for inviting me to speak here today. Good morning, everyone. Those who are in the Philippines, good evening to those who are in the US, and for everyone else abroad, magandang araw po sa inyong lahat. So what I'm going to share with you today is a story about how we use electrochemistry in order for us, or electricity for simplicity, in order for us to make compounds that are valuable in, let's say, pharmaceutical compounds, pharmaceuticals, or agrochemicals. But before I get there, I just really wanted to give you a little bit of overview that probably Marge was not able to cover. I grew up from a very big family. And that was me. I'm the 7th of 8 siblings at that time. And we grew up in Bangi, in Ilocos Norte. So if you go out of our house, this is what you'll see. So wow. Right outside our house is actually the Bangi windmill. So it's a very pretty view and inspiring for any young generations trying to get into the area of science, research, and sustainability. From there, I moved on for bachelor's, master's, and then PhD, and then postdoctoral work. And after that, I built my research group. So from the Malapit family back in Ilocos Norte to now the Malapit lab here at Northwestern. So this is us in front of the chemistry department. And this is us the entire group attending at the ACS San Francisco in fall 2023. So that's actually 1 year ago. So who are we? So this is my group. We have a good number of postdoctoral fellows and graduate students. Some of them will be graduating and becoming doctors very soon. We are coming from different places around the world. And we are also a very multidisciplinary kind of researchers. We also have undergraduate students in the lab and a couple of visiting scholars coming from around the world who are doctors and even high school students from nearby schools. So what do we do? It's actually quite an irony because growing up in Bangui, we had limited access to electricity. But now as an assistant professor, I'm using electricity in order to design organic molecules, discover reactions that has implications towards the discovery of pharmaceuticals, drug compounds, as well as agrochemicals. And I'm going to share with you one short story about this project today. The other research area is that we're putting in our expertise in organic chemistry in order for us to develop organic-based redox flow batteries. And I'm going to give you a glimpse of this work, something that's unpublished, but we are very excited about it. So I'm going to start by talking about how we use electrochemistry in order for us to discover organic reactions. This is spearheaded by two of my postdocs, Dr. Maxime Baudelaire, who is now a scientist at Merck Pharmaceuticals here in the US, and Dr. Eva Alvarez, who comes from Max Planck Institute in Germany. And so people always ask me, especially let's say here at Northwestern, my colleagues would ask me like, what is reaction discovery and why do we need to discover reactions, right? So reaction discovery is basically, we're trying to think new ways how to build molecules in such a way that we would be able to apply them in the construction of more complex compounds that could implicate drug development in the future. And the next question that I always get asked is, how would you know if a reaction is impactful or not at the discovery stage? So there could be multiple answers to that. Sometimes it depends on the bond we're forming. So as you can see here, this is a blue bond between the X, this carbon, and this Y. So if we are interested with this particular bond, then that's interesting to us. Sometimes we're looking at the starting materials. If these are chemical feedstocks, then that's also an interesting transformation. But one really thing that we are interested, especially in our laboratory, is the approach. How are we going to discover the reaction? What is the enabling technique? And is that technique going to enable the discovery of other reactions that are currently unknown today? And so I'm just going to show you one example of why reaction discovery is important. So it takes around 12 years by average to discover a small molecule drug. And the limiting step is actually chemical synthesis. And so us organic chemists plays a very pivotal role in the development of pharmaceutical compounds. And as you can see here, some sort of a timeline. In the last 50 years, we've been relying on classical organic reactions. Many of them does not really apply to a lot of the things that we wanted to do today, or they don't really allow us to discover drugs in a faster way. Today, we've been using catalysis. One example here would be a biocatalysis, transition metal catalysis, photocatalysis, in order for us to make molecules. And we've been also doing high throughput experimentations in order for us to catalyze reaction discovery and eventually the development of drugs. In the next 50 years, actually, it's already happening, is that we have been incorporating, let's say, machine learning together with the development of new reactions. So we call them molecular editing. So these are the things that we could edit molecules, at least for our case. We are transforming, for instance, this X bond into this Y bond, right? So the ability to edit a molecule precisely, especially at the late stage of the development of that particular complex compound, is extremely important in finding lead and hit compounds in medicinal chemistry. And so there are many ways how to do this. Let's say transition metal catalysis. This is something that I've been doing in the last 10 years during my PhD. For instance, at UConn, I've used a lot of transition metal catalyzed reactions, discover reactions that allow us to find novel inhibitors for serine hydrolases. During my PhD, I worked at Boehringer Ingelheim, where I developed, for example, a rhodium catalyzed reaction that uses this novel cyanation method that allows us to install a cyano group without the need of a cyanide. 3 years after we discovered this reaction, Boehringer Ingelheim actually adopted this in a multi-kilo plant, production of this Alzheimer's drug. And then during my postdoctoral work, I worked a lot on organometallic mechanisms in order for me to discover interesting reactions. And then by the end of my postdoc, I worked in data science as well as electrochemistry. And so what I'm going to share today is what exactly we're doing in my laboratory. So there are several reactions that we are trying to discover or develop to make them more selective, to make them more sustainable. But what I'm going to do is share just one example. Particularly, we are interested with how we are able to convert this carbon-hydrogen bond into an aromatic carbon-nitrogen in a very selective way using electrochemistry. So why do we want to make this bond, right? So I'm talking about this aromatic carbon-nitrogen bond, as you can see here in red. So you can see them a lot in pharmaceuticals, in process chemistry compounds, in natural products, as well as in organic materials. And in fact, with respect to drug discovery, the construction of an aromatic CN bond, just like this in celecoxib, is actually the second most used reaction in medicinal chemistry today. That is even more utilized than a Nobel-winning reaction, the Suzuki reaction that allows us to make biaryl carbon-carbon bonds. And so in thinking about when I started my career, I really wanted to be able to contribute in developing methods that allow us to construct CN bond. And hopefully that approach is going to work not only CN bond, but beyond other carbon-carbon and carbon heteroatom bonds. And so I started to think of how are we going to do it, right? Like the process or the approach. So what's really interesting to me is that if you look at organic compounds, they contain a lot of carbon-hydrogen bonds. So it's the most ubiquitous bond that you can find in organic molecules. So what I really wanted to do is convert this CH bond into a CN bond. So this would be very different than how medicinal chemistry has been doing this before or currently, because they usually make an aryl bromide or chloride. So this is usually a halide, and then do a Buchwald-Hartwig amination using palladium or nickel catalyst to introduce this carbon-nitrogen bond. But what we wanted to do is a strategy that allows us to convert a carbon-hydrogen bond to a carbon-nitrogen bond. Of course, if we are to be successful, there's going to be two fundamental challenges. The first one is selectivity. As I've mentioned earlier, CH bond is the most ubiquitous bond that you can find in many organic compounds. You can see here celecoxib, and I have labeled all the aromatic carbon-hydrogen bonds in different colors. Somehow, some of them are similar, some are not, but they are all strong aromatic carbon-hydrogen bonds. So if we are to convert or do a CH amination reaction, the question is, which of these CH bonds is going to react? So selectivity is important problem. Of course, you don't want to make 10 different aminated products, right? The second challenge would be if we are to discover a reaction that can do that, or even selectively, would this be amenable to other compounds, let's say celecoxib or other complex molecules that people have been interested in, let's say in drug developments. And so when we were thinking about a strategy, how to do this, we were inspired by nature. Nature can do so many things. There are a lot of enzymes out there that can facilitate many reactions. Unfortunately, many of these reactions are usually not applicable to the type of reactions that we wanted to do or the specific compounds that we wanted to apply it to. So Professor David Britt from UC Davis published an inorganic chemistry paper, actually, more of like a biological paper, 15 years ago, where they were trying to understand the mechanism of this specific enzyme called nitric oxide synthase. And it's been acknowledged in the literature for many years before 2010 that it involves some sort of an N plus cation pi interaction that is stabilizing a certain transition state towards its activation or its function. But in 2010, they found something unique interaction that allowed them to say this is not a cation pi interaction, but instead, they mentioned that there's actually an N-radical cation pi interaction, which is stronger than that of a cation pi interaction. And so we were inspired by this kind of interaction. Unfortunately, this does not lead to CN bond formation. So as organic chemists, what we really wanted to do is apply this kind of concept. So what we want to do is basically, can we further increase this interaction such that that interaction is so strong that it would allow us to do a charge transfer mechanism and form a carbon-nitrogen bond? So in order to do that, we looked at various types of nitrogen-centered radicals, right? So here are some examples. So there's one here. This is an uncharged. It's a neutral N radical. And calculations have been done that the electron affinity of a neutral N radical is around 3.7 electron volts. If it's a cationic N radical, it increases. And this electron affinity is somewhat analogous to its electrophilicity. So we are looking for an N radical that looks like this, where you have two cations, a dicationic N radical, because it has a very high electron affinity, and this will allow us to strengthen this radical cation pi interaction, and hopefully it leads to a charge transfer and CN bond formation. And so from there, we were really inspired by how can we make this highly electrophilic and reactive N-centered radical. So my postdoc, Ava, has looked into the literature and tried a lot of experimentations. So for the students out there, this usually takes months, sometimes years, or sometimes we end up not discovering any, right? And so what she found that if you use a select fluor, which at least during that time, it's used as a fluorinating reagent, but we could actually reduce select fluor, it's a commercial reagent, and generate this, at least as we propose, a dicationic N radical that resembles exactly the dicationic N radical that I've shown in the previous slide. And if we are to generate this electrochemically and we throw in an aromatic system that contains a carbon-hydrogen bond, we were expecting to have a strong radical cation pi interaction. And hopefully it leads to a charge transfer. And so we set up this reaction under electrochemical reactors. And this is what we found. We can generate this product. As you can see, this carbon-hydrogen bond is now converted to this aromatic carbon-nitrogen. We call these compounds aryl dibconium salts. And the synthetic community seem to have liked that because this is a Dabco unit with excellent yields. So usually we obtain greater than 90% product yields, but the selectivity is unprecedented. As you can see, it's 23:1:1 selectivity towards the para CH position versus the ortho and the meta. This is some sort of unheard selectivity for a non-directed CH functionalization. And not to mention, we're not using any special catalyst here. We're just using electricity and carefully choosing reagent and the approach of making this CN bond. And so the next thing we always do is look at the mechanism, right? Try to understand how it happens. And as I've mentioned earlier, we are proposing that we're generating this radical cation pi interaction as a driving force. And we then propose that it undergoes a charge transfer followed by a subsequent CN bond formation. So you'll get an aromatic radical intermediate P. And then the other electrode on the other side, because this is an undivided cell, would oxidize that to this positively charged intermediate, Wieland intermediate C. And then in the presence of a base, as you can see, base is the only additive. Triethylamine, it would deprotonate this and you regenerate the aromatic system and form this carbon-nitrogen bond. So this is so efficient because the next question is, we just discovered a highly selective reaction, but as I've mentioned earlier, the other fundamental challenge is the scope, right? Is this going to work to other aromatic CH bonds? And here I'm just showing a display of some of the compounds that we have tried. As you can see, we can tolerate aryl fluorides, bromides, chlorides. These are systems that you would usually use in a lot of transition metal catalysis. We can tolerate some electron-rich and a little bit of some deficient substituents. We can tolerate a lot of heterocycles. And sometimes if we have two different arenes, it's actually the most electron-rich arene that would react. We could tolerate a lot of heterocyclic compounds, as you can see here, a display of pyridines, bipyridines, terpyridines, and these are some of common ligands that people use in transition metal catalysis. So we are advancing the field of CH functionalization. with this transformation. So this next slide is something that I'm not going to go through. There's too much chemistry and science in here. But the next question that we always ask after we discover and display that the reaction works very well in a synthetic application, we want to understand the mechanism, which is basically how did this newly discovered reaction work, right? And what I've shown earlier is just some sort of a proposal. And what we're trying to do here is experimentally validate that. And so we collaborated with Professor Osvaldo Gutierrez at Texas A&M. Their expertise is on DFT calculations. So what they did for us is calculate the energy required in order for, let's say, the radical cation pi interaction, the energy of that, the energy of the charge transfer, the energy of the CN bond formation. And they tell us that they are all very low energy transformations, or all the transition states involved are very low in energy. So it kind of gives us an idea that our proposal is most likely correct. Here's another example of a mechanistic study. Here we're using cyclic voltammetry as a technique in order for us to characterize what we've been claiming as radical cation pi interaction. So once you oxidize or reduce select fluor, and you're gonna get the N radical cation, this is a very reactive intermediate. So what we're doing here is reducing that and adding different arenes. And as you can see, we would see a very characteristic anodic shift, denoting that we are stabilizing that N radical cation, and we could propose some sort of a mechanism based on that observation. My favorite mechanistic study is probably this. So when we develop a reaction, one question is selectivity. And we have demonstrated that our reaction is indeed very selective. But what's really interesting, especially when we try to apply this to, let's say, medicinal chemistry, let's say someone wanted to use celecoxib as a substrate, right, which contains more than 10 different CH bonds. How will we know which of the CH bond in celecoxib would undergo CH amination, right? We know that there's probably just going to be one product, but which CH bond? And so our computational chemist collaborator came up with an idea that if they calculate what we call a Fukui index, which is some sort of related to how electron-rich a carbon is on the aromatic system. And the higher the Fukui index, the more nucleophilic or electron-rich that carbon is. So for instance, here, this is fluorobenzene. As you can see here in red, the Fukui index for this carbon is 2.3, much, much larger than the other carbons. And the other substrates that I demonstrate here, they are always 10 times or 20 times larger in Fukui index than the other carbons. And if we calculate these Fukui indices and perform this CH amination reaction with these substrates, this is where we observed CH amination products. So not only our reaction is selective, but we could actually predict which CH bond reacts. And that kind of lets me go back to one of my favorite compounds here that I've shown at the beginning earlier. This is celecoxib. It's a blockbuster drug 10 years ago. So as you can see, there are different CH bonds. And so it would be very hard to select which CH bond is going to work, right? So if we subject this into our electrochemical reaction, you can see here compound 19, we could convert selectively this CH bond here, the one in blue, into a CN bond, which to us is extremely amazing. And you will only get one product in 92% yield. So we tested that with a lot of other known pharmaceutical drugs like fenofibrate, florbiprofen, bifenazole. So we call this a late stage functionalization because you are using a drug itself, put it in your reaction, and we are exclusively generating one regioisomeric product in all of these complex compounds. Amazing, right? And so when we do the CH amination, the first product that we obtain is actually this compound that we call as aryl dubconium salt. And of course, practitioners in organic synthesis would not be interested with what is this compound, right? But it does have a CN bond, which is great. So one of the tasks that we had early on is how can we discover reactions of this aryl dubconium salt in such a way that we could convert a net CH amination and at the same time generate other products out of it. So I'm just going to give you some examples of how we use aryl dubconium salt. So after the reaction is done, all we need to do is stop the electrochemistry and then add in a base or a nucleophile. This will open up most of the time the dubconium salt and liberate different types of aryl piperazines, as you can see here. And aryl piperazines are actually, or piperazines are the third most frequently found nitrogen heterocycles in FDA-approved drugs today. So one interesting reactivity of aryl dubconium is that we could actually cleave this CN bond using a photocatalytic reaction. So we could convert this into aryl radicals by reducing them in a 1-electron reduction procedure. And we can convert them directly to a carbon-carbon bond, as you can see here in the construction of these bonds here between the red and the blue aromatics, or we could make carbon-phosphorus bonds. So this is amazing because we can start with CH, form different CN bonds, as well as CC and C phosphorus bonds. And so this is just to summarize what I've shown you today. We have developed an electrochemical CH amination that operates via a radical cation pi interaction, which to us it's very enabling. It generates a very radioselective CH amination product, as well as carbon phosphorus and carbon-carbon bonds. This was published last February in the Journal of American Chemical Society, and we are really glad that this actually had a lot of great impressions from the scientific community. So it's been highlighted to a lot of news articles as well as scientific journals. So if you really wanted to know more details about this, we have actually a lecture on YouTube. So my postdoc Eva is giving a YouTube lecture about this specific reaction, both in English and Spanish. So just check that out. It's called Synthesis Workshop. And so where do we go from here? Of course, we have been doing a lot of things. So we are generating CN bonds that are different from a dubconium. So can we go beyond dubconium, right? Because we're kind of limited with that framework. And the question is, can we go beyond CN bond formation? For instance, can we make CS, CP, or CB directly from a CH bond? And of course, further expand the reactivity of the aryl dubconium salts. Okay, so I'm going to stop the first story there. And what I'm going to do now is just quickly go over an amazing project that we just started 2 years ago. So as you can see, my career path has always been in the development of organic reactions. But 2 years ago, when I started at Northwestern, two of my graduate students, Emily Mahoney and Ann Kitamura, were very excited about joining my group, but they really wanted to do something that relates to sustainability. How can we use organic chemistry and electrochemistry for sustainable type of research? And so one of the area that we identified where we could actually put in our expertise is in the area of organic redox flow batteries. And so why do we need to develop batteries? So there are a lot of different batteries based on the design, based on its application, based on the material that's stored or that's present in your battery. But the battery that we wanted to develop is not the battery that you use for your cell phones or laptop or your cars. What we wanted to discover is a grid scale battery, a battery that looks like a football stadium. So a very big battery that allows us to store as many energy coming from the sun or the wind. And this battery could allow us to power not only a cell phone, but an entire city. And there are a lot of challenges in here. And this is actually one of the missing piece in order for us to really start relying on renewable sources. So we have renewable energy sources, just like wind, water, and solar. And we do have ways to capture them, let's say by solar panels or windmills. But we usually don't directly connect them to our households or instruments because there are fluctuations. And sometimes, in fact, there was a study that when the solar energy is high, it's actually the time where we are away from home and the energy consumption in households is actually at the lowest. So what we need or what's missing in this equation is a large battery that's enough to store as much energy from from your renewable energy sources and then be able to use that. So there are a lot of technologies out there being developed in the last 50 years. And one of the things that we found really interesting is we call it a redox flow battery. So from the word itself, there is some redox happening, reduction in oxidations, and there's a flow. We are flowing redox active compounds. So as you can see in this picture here, so this is your electrochemical cell. This is where you're going to do the electrochemistry. So this is where charging and discharging would happen. And then these are tanks. These tanks, they contain redox active compounds. We call them catholytes. These are the compounds that undergo oxidation during charging. These are called the anolytes. They undergo reduction during charging. So what's really interesting about redox flow battery compared to other battery systems is that you could decouple power and energy because power comes from For instance, the electrochemical cells, you just have to increase more electrochemical cell stack. And if you want to increase the energy density, you just have to add more tanks. And you can't do that by design with other grid scale type batteries out there. So you might be wondering, is redox flow battery happening? I mean, Barack Obama, when he was the president, he always talks a lot about redox flow battery. And I've heard from the Department of Science and Technology in the Philippines that they're actually working on redox flow battery for the Philippines. And so the state of the art uses vanadium. So this is vanadium metal, right? So in your tanks, what you have here is a vanadium metal that gets oxidized from vanadium 2 to 3 when being charged. And then reduced is a vanadium, sorry, oxidized is vanadium 4 to 5, and then reduced during discharge. So it uses 2 vanadium molecules on both sides of the tanks. Here's the problem with vanadium. Although it's working, it's actually great. So the largest vanadium redox flow battery installed in the US is present in San Diego. So this could actually power 100 households for 4 hours. But the largest in the world is found in China. It's a 400 megawatt hour capacity. So that's almost 10 times the capacity of what you can find here in San Diego. So there are 2 fundamental challenges with vanadium redox flow battery. First, vanadium is mined. And since vanadium redox flow battery became commercialized about 10, 20 years ago, it's becoming more and more expensive. Second, there's not enough vanadium in the world. If we are to extract all the vanadium on Earth's crust, it's only going to be enough. It's not even going to be enough to provide a vanadium redox flow battery for the richest 1% population of the world. And the second fundamental problem is that it has a very low energy density. And energy density is directly proportional to a lot of things. One of them is U. And U here is the open circuit potential. So this is the redox potential of the 2 redox active species in your tank. And for vanadium, U is equivalent to 1.26. That's the difference of the redox potential of these 2 species here. So what we wanted to do here is replace vanadium with compounds that has more positive and more negative redox potentials, such that the potential difference is going to double or quadruple that of vanadium. So that would quadruple the energy density automatically of your redox flow battery. So before we started in this area, there's been a lot of work in the last 10 years where people have looked at organic molecules such as these compounds here. But one drawback is that they have only developed organic compounds that are soluble in water. And vanadium, which is the state of the art, is actually operating in a water solvent. And the problem with water solvent is that water itself undergoes oxidation at around 1 volts, undergoes reduction at around -1 volts, which means that you are limited by this solvent window. If you wanted to go beyond +1 or -1, you're starting to oxidize and reduce water. And that's basically a water splitting. You're generating hydrogen gas, and that causes this battery to explode or become flammable. But again, you can't go beyond 2 volts with that idea. So what we wanted to do is change the water solvent into something organic, because a lot of organic solvents, for example, DCM, for example, acetonitrile or DMF, has very large redox potential window. For instance, they could go beyond -3 to +3. So that would be 6 volt of a difference. So that's where we are playing right now, right? So that's automatically 4 times possibility of increasing the energy density of a vanadium redox versus vanadium redox flow battery. And in the last 5 years, people have looked at some molecules, but as you can see, they're kind of crazy looking, right? And mainly because it takes a lot of synthesis and development, and they're usually not sustainable. So when we entered in this area, what we wanted to do is find molecules that are sustainably sourced. So this slide is just showing us how challenging this pursuit is, because if we start with one molecule, let's say it has a great redox potential, let's say very negative, but then it's not stable, right? So it's not good, because you don't want a battery that dies in a day. You want a battery that would last for 2 decades, right? So you want to be able to charge and discharge a battery that looks like the size of a football stadium. Solubility is important because concentration is directly proportional to energy density. If we could develop compounds that can do multiple electrons, that automatically doubles the energy density as well. So as organic chemists, we are poised to be able to discover organic compounds that could fit into a lot of these things. But what I'm going to show is something that fits into a very good or very negative redox potential and a very high stability in order for us to double or quadruple the energy density of an organic-based redox flow battery. So the central theme in our group is to find compounds that are sustainably sourced. So we wanted compounds that you can just find in biomass or compounds that are actually industrial wastes. So we were really interested with triphenyl phosphine oxide. This is a very painful organic waste. So if you are an organic or synthetic chemist, you probably have worked with this. They're usually difficult to separate. And unfortunately, they are generated in stoichiometric amount in many industrial processes, and they have no purpose. So they have no use. So BASF is the company that generates a lot of triphenyl phosphine oxide, and they're actually using electrochemistry to reduce it back to the phosphine, but they said that process is more energy intensive than just basically buying a new phosphine. So what we do as a concept is we are applying molecular engineering, right? So we redesign this compound molecularly and generate a new compound, right? So I'm just showing you here what we found out. We have formed a bond between here. It looks very simple, but it took us forever, 2 years actually, to find that this is the one that works. So we call this the CPO. It's a cyclic phosphine oxide. It can be synthesized in one step from the triple phosphine oxide. It has a very stable redox potential and a very negative reduction potential at around negative 2.4 volts. And so this is just a story of how we started from TPPO to a lot of libraries. These are usually tens, 20s to hundreds of compounds until we ended up with the perfect compound. And as you can see, from an irreversible phosphine oxide to a quasi-reversible to the green compound, which is a very reversible cyclic phosphine oxide. And as I've mentioned earlier, you can make this from the waste itself in large scale. And so we do a lot of mechanistic studies. For example, we can reduce it in a 1 electron and generate this radical anion, and we could actually isolate that radical anion, analyze them by X-ray crystal structure. This is the second isolated crystal structure of a radical phosphine oxide. And this is just an APR analysis in order for us to quantify or qualify that particular radical. Okay, so this is what we do next. Once we have a hit compound, we now start to do cycling, and then after that, we use them in a flow battery. But these are usually very small amounts. So these are like 5 to 10 ml solutions. We're not working with a 1 liter solution at this point yet. So what we do is we charge the phosphine oxide, and then we discharge. So you fully charge and then you discharge. And what we see is the capacity here. So when you charge, you record a capacity. When you discharge, you report a capacity back. And as you can see, it works very well. In DMF, after 50 or 60 cycles, the capacity now starts to fade. So something's going on, right? If you do it in acetonitrile, the fade is faster. So you don't want this kind of performance because it means that probably after 10 days of using the battery, it's going to die. But if we could use or modify, let's say, the supporting electrolyte, we could actually make them even better. But after 100, this usually dies as well. So we perform a lot of mechanistic studies. So for instance, we generate the radical anion electrochemically or chemically, and then we understand what's happening. In DMF, we found that it's actually decomposing to a compound that we don't know yet. But this is the decomposition pathway. In acetonitrile, surprisingly, it decomposes to a completely different compound. So that tells us a lot of knowledge on how it's decomposing, and then it's giving us information how to solve this problem. So what we wanted to have is a system wherein this compound would last for 100 or 1,000 of a cycles. So after a lot of studies, and I'm not going to go through what we went through, how to make that to work, but basically my student, Emily, found that if she will use actually 40% acetonitrile in DMF and applying 80% of state of charge, so we're just charging at 80% rather than 90 or 100%, and then we could cycle this. So this is an experiment that lasted over Christmas, actually. So we discharge, and this could be usually like 10 cycles is usually like 2 to 3 weeks. 300 cycles is usually 1 to 2 months. So these are very long experiments. And as you can see, the compound never died. It does not fade. We're still getting a capacity fade of almost 0, negligible. And so I'm going to end there. And I hope that I was able to give you a story and how an organic chemist like our group could participate in a lot of important scientific and research pursuit. For instance, how we utilize our expertise in organic chemistry and electrochemistry to discover new reactions that are not present in today's literature. make them selective, and hopefully apply them in pharmaceutical developments. That as organic chemists, we could actually also contribute in the area of sustainability for this case, the development of novel and next generation organic-based redox flow batteries. I really want to thank my group. They have done all the work, especially Dr. Eva Alvarez, who initiated the CH Amination project, graduate students Ann Kitamura and Emily, who started the phosphinoxide or the redox flow battery projects. And I want to thank our funding from Northwestern and NIH, National Science Foundation, and our collaborators at Merck, Texas A&M, and here at Northwestern. And with that, I can take any question, and hopefully I did well on time. Thank you all.
Okay, thank you very much, Christian. And also thank you for sharing your story. I actually wanted to do that. And I'm glad you included the pictures from your webpage, because every time I look at it, I always get a warm feeling that there's this happy group of people doing exciting science together. So thanks for doing that. Right now we are open for questions. If anybody has questions for Christian, please either you can type it in the chat box, or you can actually just raise your hands and speak. Open your make sure you open your video when you do that, so that we can see you when you ask your questions. Oh, okay. Toby has a Dr. Direct has a question.
Yeah, Christian, yeah, congratulations for all your great work. Well, maybe I just comment that it's really great that you're able to collaborate and work hard. I think that's a very good lesson for everyone who wants to start a group. Maybe no more technical question. I'm interested in your slide number 19, because you gave the energy diagrams, and the energies don't seem to be very much different. So I'm wondering how the selectivity arises.
Are we looking at the DFT calculation, right?
Yeah. That is a very interesting energy diagram on the left.
Yeah, I mean, an energy difference of around 1 to 2 to 3 is definitely low. I think what we have here is a selectivity towards blue, right? So this is the para position. So it's a energy difference from.
So I guess my question is that it looks like that's enough to give you selectivity with a very small. Yeah, that's amazing.
It is. And this is something that people have looked at in other systems before, that they're actually kind of all very low barriers. And I think this is where electrochemistry comes in, because when we say electrochemistry, people would always think that it's very similar to photochemistry, but it's not. Because when you do photochemistry, you are basically getting all your reagents activated at the same time, right? All happening. But in electrochemistry, you are generating very small amount every time at the surface of the electrode. So it's a very catalytic generation of the reactive and radical cation for this case. And then throwing in, usually we can operate with amine as the limiting, the arene as the limiting reagent. But yeah, that's a really great observation. For this case, we have used toluene here, and toluene is not one of our most selective substrates. Because actually, the more electron deficient the system is, the more biased the Foucault indices of these carbons.
Yeah, that's great.
But I think the reason why we ended up with toluene as the substrate is because it's the one that gave us the best radical cation pi interaction when they did the calculation. But that's a very great observation, and thank you.
Yeah, thank you. Yeah, you're giving organic chemistry a good name. So yeah, thanks. Congratulations.
Thanks, Toby.
Okay, do you have any other questions?
I have a follow-up question on this same slide. This is Gladys. Okay. Again, first of all, congratulations, Christian, for doing a great job. And so Very similar to what Dr. Dairit mentioned. So you mentioned about the Fukui indices. So how reliable is this? Because I noticed nga this is a para position. So did you try? So I noticed you try different substituents where there are election releasing groups, election donating groups. So how predictable is this for Fukui? How did you, is that the right pronunciation?
Yeah,
Index?
Fukui.
Yeah. How?
Yeah. So calculating the Fukui index according to our collaborator is actually very easy. So they can do that in a day for 10 or 20 compounds. And so we just gave them a lot of compounds. So they probably sent us back around 30 different arenes that we have tried and did not try. And they have all been matching. So we have a very interesting substrate. If this is a CF3,
Mhm.
the Fukui index goes to the meta position. That's the favored one. And that's what we also observed,
That's nice.
which I think is a very interesting indicator. And we also gave them some complex molecules after that.
Okay. So what you've tried so far are all commercially available substrate, right?
Yes, yes. Some of them we might need to do some protections. But here we wanted to use something that we don't need to protect, right? The functionalities, because we really wanted to demonstrate that they would work. I think this is the one that we protected, fluorbiprofen methyl ester, because fluorbiprofen is just a carboxylic acid, and we could not tolerate a free carboxylic acid yet. But yes, we tested a lot of anything that we can buy.
Yes. So just a follow-up question. So based on your Jack's paper, I was only able to read the abstract. Could you send us a copy of the full paper? I don't have access to that. So so far, since I noticed the some yields are really not that great. So what are the hurdles that you have encountered, or what is the limiting for you to, so that's why the yields are not that great?
Yeah. Oh, this is a very good question. I would say that the yields of the CH amination is great with our standard. So they are the yields in parentheses. So here, for example, this is a quantitative yield. So almost 100%, 98%, 98. And once we get into a little more complex compounds like this sulfur nitrogen containing compounds, people usually can't functionalize this in many other ways, but we can. And so these yields that we're getting are already high compared to that kind of standard. And the yield outside the parentheses are the yields after the second step. So if the yield, for instance, is 82, that's in two-step reaction. And also to go back, I think you mentioned about what makes the reaction low yielding, right? So we have a paper that we submitted recently in a great journal, and hopefully we'll get a positive response. So it starts with this story, but what we're doing is a mechanistically different approach. So instead of generating this DABCO from select fluor, because that's a limitation, right? So select fluor, that's the only component that we could add. The question is, can we add different types of nitrogens so we don't have to rely on select fluor? So could we just use a normal amine, like a cyclic amine, and generate the same intermediate? So we would have to oxidize it. So under oxidation pathway, it will still undergo the same mechanism, but it could now functionalize highly electron deficient systems. So I'm going to go back to our scope. As you can see, we did not show a cyano. We did not show a nitro group. And there are no functionalizations that can do those. In fact, if we think about our organic chemistry, sophomore organic chemistry, if we do this nitration, right? Friedel-Crafts halogenation, like those kind of electrophilic aromatic substitution, it only works with electron-rich system. They don't work with nitrobenzene, right? So you can do nitration with or halogenation with electron deficient. So that's also the same problem that we're having here, because mechanistically they're kind of somewhat different. But with that new approach, which we had it submitted recently, we can now functionalize nitrobenzene, benzonitrile, a lot of highly electron deficient systems that today no one has ever done. I apologize, I did not show you those. I did not know. we are gonna end up going to those details. That's why your question, Gladys, is like so amazing. So yeah, we have a work that we have been developing for quite some time now. And the good news as well is we just did not only expand the arene, we also expanded the amine because we are not limited to this kind of framework. So when it comes out, I will send the news.
Yeah, thank you. And share the full paper, please, so that I can share it to my organic students. So thank you for my students who attended here. And then I like your aryl dubconium salt term. Okay, so that's very nice. One more question. Sorry, Marge.
Yeah.
For
But
your
it's okay because you're asking really good questions.
so the vanadium catalyzed battery. So aside from that, so you gave all the limitations of in terms of the resources of vanadium and a low electron density. Aside from vanadium, are you trying to explore other battery?
Yeah, so the state of the art is vanadium, and people have looked at lithium as well in flow. People have looked at nickel, chromium. Actually, chromium was the first one that was discovered in 1960s, but of course, there's a lot of toxicity and resources challenges there. There are a lot of people looking at other metals or combination of metals. That's not our territory. So what we're working on is on the organic, like changing vanadium with an organic molecule. As organic chemists, I feel like that's where we could bring in something. So yeah, there are a lot of things people have looked at, but vanadium would be the most stable under if we're talking about metals.
All right. Thank you very much, Soki. Maybe there are other questions. Thank you.
Do we have other questions from the audience? I know that there are students from Gladys' class in here, so we really encourage the students to ask questions. This is your opportunity to ask Christian these questions and answer you personally. So my other question with respect to your organic batteries that you're developing. So you're talking about football size batteries that you're gonna use for this. So in terms of I know that you're using some waste material as a starting point for generating your batteries. Is that abundant enough that you know that you can have sustainability for many years for this kind of process if that comes to fruition? I think you're muted.
Okay, I get. That's a great question. So right now with the phosphine oxide, if we partner it with a right analyte that is also very positive, then we could quadruple the energy density compared to vanadium. So if this is a vanadium battery, that means to supply the same amount to a city, we just need a quarter of the size, right? If we want to supply the same energy. And what's really interesting with our phosphine oxide is that we could actually do a 2-electron system, but it's still unstable at this point. We are working on stabilizing that molecule, but we can do 2-electron system. So that would, I don't know what's 8, but about 8 times the energy density of vanadium. That's what we're looking at in the future. And so, so yeah, then that means that the size becomes lower and lower depending on how much you want it, right? But there's always been a pursuit in extremely high energy density for many reasons. We wanted something like, okay, if you have like a car size battery, so this would be batteries that you could use in, let's say, military operations where they don't have a lot of supply of electricity. This would be some sort of a super battery that people could use in space, right? In space shuttles. So those are the things that other people are looking at. And we started a collaboration here at Northwestern and Argonne, where we're looking at compounds that could actually do 12 electrons in one molecule. But of course, there's going to be a lot of challenge happening there. But if we could make those to work, then they would have extremely high potential for applications, not only for the Earth, but outside Earth.
Great. So this will be the next generation batteries for many purposes.
Yes.
Cool. That's very, very cool. Do we have any other questions? Billy, you go ahead, Gladys.
No, it's okay. Go ahead. Is Billy asking a question?
No, he always asks questions. That's why I call on him. But anyway, go ahead, Gladys.
So how was this different? So this is not actually related to to your research work, but I was just wondering, since there are students here, are you accepting graduate students right now? Is your lab open to that for, Filipinos who are aspiring to do graduate work abroad? So can they just email you and then contact you?
Yeah, no, definitely every year we're looking for the best students wherever they're coming from. And feel free to contact me. Of course, there are requirements. Be an outstanding student, be driven, be passionate, and be someone who really wanted to do research, right? And we are situated in a great university and great chemistry program. And more importantly, Chicago is one of the most beautiful cities in America. So
It's one of my favorite
to answer
cities.
the question, yeah.
Yes,
When I
and
was in Ann Arbor, Michigan, we always visited there twice a year just because
Chicago.
it's so beautiful. Yeah.
then you should also consider doing balik scientist program so that you can, share what you've been doing, transfer the technology, hopefully, especially this vanadium catalyzed battery. So I think that would be great. So yes. And then there is also a scholarship program, the DOST scholarship program, where graduate students can pursue PhD abroad, and then the Philippine government DOST will finance it. So I hope you'll be open to that as well,
Oh,
Christian.
that would be really great because, of course, funding is usually the biggest challenge, especially in the US, because grad students are quite expensive here.
Yeah.
And so, yeah, someone who would have a fellowship, even though it's partial, that would give them much higher chances to get into not only in my lab, but anywhere here in the
Anyway,
US.
There you go. So I hope you inspired definitely you inspired a lot of the students here. So having said that, we will invite you to be a speaker again next year in our STEAM orientation to inspire high school students.
yes,
And
we need to do that. But I also told Christian that well, I invited him to the APAMS here in South Carolina for one thing. But I think the next APAMS in the Philippines, if we continue with our write shops and workshops with the
Yeah.
students, that's gonna happen in 2026. So that is another thing that we could all attend. I don't know if Christian know about your crazy idea last summer where we went to 4 different locations in the
crazy.
Philippines. We had a
Yeah.
caravan and
Wow,
did
I did not
workshops.
hear about that. Yeah. Well,
Yeah.
I would
We did
like to join and
workshops.
participate in the most that I can, right? And
Yeah,
hopefully this bring in fruitful collaborations, especially
right.
sending students in or visiting students, I think that would be really great for us. We did have some Filipino grad students here at Northwestern. I don't know if there's one actively right now, but these were actually Filipinos who grew up in the US, not
Mhm.
directly coming from the Philippines. And I would love to have someone who comes from the Philippines to, show my colleagues here how amazing we are.
Yes,
Right.
definitely.
I
Yes.
think Billy.
So now Billy is raising his hand. So Billy, take it away, Billy.
Yes, again, excuse this very, very simple question. I start that, a couple of my children are at Northwestern, and my the first grandchild is there, uh, trying to get to a pre-med course and all of that. So Northwestern is something else. Uh, so batteries. First, there was the lead battery, and then I was intrigued about your use of organic chemicals as the source of the chemical reaction to get the energy. And then you mentioned vanade lithium is there, but it's getting scarce, I believe. And
That
then
is
you mentioned vanadium, which you said may also getting scarce. Then you mentioned about CPO from waste products. I did not get what chemicals are there from CPO that you are using in
yeah.
this biochemical reaction that produces electricity.
Yeah, so there is this chemical waste called triphenylphosphine oxide. It's the oxidized form of triphenylphosphine. And there are a lot of organic reactions like Apple reactions, Wittig reactions, and trifluorophosphine oxide is a stoichiometric waste of industrial organic transformations that people produce in a lot of amounts. So BASF is the biggest contributor in generating trifluorophosphine oxide as a waste. The interesting about trifluorophosphine oxide is that it has no value. It has no application. So it's just a waste. So they just, I don't know, they just burn it out or probably throw it somewhere. Although there's been a lot of research being done around the world, especially in Europe, on how to convert them back to the phosphine, because the phosphine is the one that you use in a reagent, as a reagent for the reaction. But it's a very energy intensive process that BASF would have to spend more money rather than just buying a pure triphenylphosphine. And so we got really interested with triphenylphosphine oxide as a starting point because Alan Bard, a great electrochemist, found or showed a CV that it has a very negative potential, around negative 2.5 volts, in a publication in 1965. So that's where we started. But it's not reversible. So if we use triphenylphosphate oxide itself as the analyte for our battery, it charges and then it dies. It does not discharge. So it doesn't even do one cycle, right? And so the approach that we do in our lab is called molecular engineering. So we don't do biological, but we do organic chemistry. We basically make analogs of that, right? So we made different types of phosphine oxides, and it turns out that CPO, the cyclic version of trifluorophosphine oxide, gave the best performance. And then from there, we found that we could actually synthesize CPO from trifluorophosphine oxide in just one step. And we can do this in multi-gram scale, at least we've done 13 grams. So to us, that's really promising. And the fact that it has a very negative potential, it will be the first reported in the literature to be the most negative. So our paper is actually under revision in JAX. So hopefully it will come out soon. And we have a patent that we submitted recently.
Great. Wow, that's impressive.
Wow. Thank you. Oh,
Thank you, Billy. There is a question on the chat from Nathan Kelsey Omandam. The question is, given that there are green chemistry regulations in prohibiting the use of certain organic solvents, I would like to ask what factors must you consider in choosing which organic solvents to use?
That's a very good question, especially for where we are going on right now. So as I've shown in our discovery, we needed to use acetonitrile and DMF, and these are the standard, at least for the discovery phase. But I don't think that they would be the best one to use for application itself. So people have been looking at polycarbonates. So these are more sustainable types and non-toxic organic compounds. So the good thing about it is that since they're less toxic, they have lower safety, they're better safety parameters compared to water, because vanadium uses water, and if you hit the oxidation or reduction of water, it will generate hydrogen gas. But polycarbonate would not, right? And polycarbonates are actually being used right now in different types of lithium-ion batteries. So that's where we're headed. So as organic chemists, we are contributing on developing novel organic compounds, but there are actually a lot of engineers out there. There are a lot of green chemistry and environmental chemists or scientists who are developing membranes, because you need a membrane, right? So we also have environmentalists looking for other alternative solvents. So yeah, at the discovery phase, we use what works best to discover, but then towards application, we probably needed to end up with something else. So that's a very good question.
Okay, thank you so much. Okay, so I don't see any questions in here. And Feb, do you see any questions? We are also live streaming on Facebook, but so I don't see. I'm trying to check.
Can I just
Yeah?
No
comment,
question po,
Marge and Christian? Can I just
Yeah.
make a special comment? So Christian, yes, I've worked with triphenylphosphine oxide. It's a nasty compound to really get rid of.
Remove, yeah.
Yeah, so that's why thank you for coming up with that reaction to convert
It's
it.
tricks in column. Yeah, it's tricks in column.
Yes, it's so
Yes.
difficult to remove. Okay, yes, again, I think congratulations.
Yeah. Really. Okay, so I don't see any more questions. I don't see questions on. We're live streaming, but I don't see questions there. There are people on the live stream. But anyway, I would like to take this opportunity to thank Christian for this very exciting and really novel and innovative research that he's carrying on in his lab. And so we would like to hear from you in the future again and hear where this is going. I am sure that this will be groundbreaking. There are more groundbreaking discoveries coming for your lab, considering you only started when, in 2022? So there's more coming up, I'm sure of that. So please join me again in thanking Christian for this very exciting webinar today. And so we are, Fab, can you give me the slides? I guess, Christian, we need to stop sharing from your slides and get the slides from Fab.
Actually, she was showing it already. Can you show
Oh,
the
she is. Okay.
certificate first? Could you please show the certificate first, Fab?
Okay, Fab, can we have the certificate? Hello?
She was
I have
already.
So, okay. So, all right. So we have a certificate of appreciation that we're going to read to you for presenting this webinar. And we will also email this to you. So basically, a certificate of appreciation is presented to Christian A. Malapit, PhD, for being our speaker at the Philippine American Academy of Science and Engineering PAASE webinar entitled Synthesis and Electrochemistry for Reaction, Discovery, and Energy Storage, held on November 8, 2024. Presented this day, November 8, 2024, with our deepest gratitude. Signed, Dr. Gladys Cheris Completo, our president of PAASE. And so, Christian, this is for you, and we will mail this to you. Thank you very much again for this very exciting talk that you gave us today. Okay, so like I mentioned, this webinar takes place, our webinars takes place every 2 weeks on Friday mornings in the Philippines and Thursday evenings here in the United States. They are actually live streaming also in Facebook. And also, this is recorded and it will be posted on the PAASE YouTube channel. And so even though we have about 31 people attending today, this is going to be viewed over and over again by other people. And I've heard that sometimes it goes up in the hundreds, depending, particularly since we have students viewing this webinar today. And so now I want to take the opportunity to announce the next webinar that is coming up in 2 weeks. Friday, November 22 in the Philippines at 8:30 a.m. Thursday, November 21 at 7:30 p.m. here in the U.S. And this will be Dr. Neil Concebido, a certified process safety professional. He is going to talk about his Balik scientist journey, promoting process safety management in the Philippine universities. So we would like to invite everybody to attend this webinar in the next 2 weeks. And then we take a break. We specifically took a break for Thanksgiving because we don't want, I guess, people will be eating turkey in the United States. Our final webinar for the year will be on December 6th, Friday, 8:30 a.m., December 5 in the United States. And this will be presented by Dr. Aristotle Ubando, PhD, who is Assistant Dean for Research and Advanced Studies and full professor and research fellow at the Gokongwei College of Engineering at Salle University. He is the founding head of Thermomechanical Analysis Laboratory, or TALA, from De La Salle University, Laguna, Philippines. And he will present a talk on an application of fuzzy set theory on the sustainable production of microalgal biofuels. Again, another two seminars coming up that are also very interesting. And then after this webinar, we will have, save the date, December 13, 2024, will be the year-end event and Christmas celebration of PAASE. And so this will take place 9 a.m. Friday in the Philippines by Zoom. This is actually my birthday, Gladys. I didn't tell you that. But
we're gonna
that's
celebrate.
we're celebrating my birthday. So we invite everybody to this event. We will have games, activities, singing, engagement, and then we will present awards to those members who have done outstanding service to PAASE. So please be there and join us in this Christmas celebration, year-end celebration. And then also I will take this opportunity to announce APAMS 2025. This will take place, save the date. This will take place at the University of South Carolina here in Columbia. This is where I am. You'll come to my place and we would like to welcome you to Columbia. This will take place on July 18, 19, 2025. We will start with a welcome event and a mixer on the evening of July 17th. And there is the possibility of an excursion to one of our plantations here and one of our famous city of the South, the New York of the South, which is Charleston, South Carolina. So we invite you to that. We're looking forward to this event. And so with that, I would like to thank Christian again for giving us this opportunity, for this time, and sharing your research with us. And so see you all again in the next webinar.
Can we have a photo op for
Okay, so everybody, can you please
else?
open your slides? We still have 31 people here. Naku, nandito pa lahat, hindi umalis.
Very much. And thank you
So,
for
can you
attending.
please open your cameras so that we can have... Feb, are you ready with the picture?
Yes po. Sige po. 1, 2, 3.
Smile na kayong lahat. Kailangan makita mga mukha.
Yes, so you
Smile.
pictures first.
Yan. Fix your hair. Put your smile on. All right.
Page 2 po. 1, 2, 3. Smile. Okay na po.
Okay. All right. Thank you everyone for attending. This is very nice. Okay.
Thank you.
Thank you
And
very much. Thank you, Mark.
thank you, Christian. Thank you, Billy.
Okay.
Thank you,
Thank you,
Toby.
Dr. Marge and
Yeah,
Gladys.
bye. Thank you. Thank you.
Yeah.
Thanks
Send
for
me
coming,
the-
Dr.
Christian, can you please send the paper, okay? The Jack's paper.
I will. Yes.
Thanks
thank
very
you.
much. Okay, bye. Thank you, Marge. So see you
Yeah.
2 weeks from now. I'll moderate
Okay.
that. Niels,
Oh, you'll moderate one. Okay, great. Awesome. Okay.
thanks. Okay, bye.
Applause. Okay, bye.